Hi friends, welcome back to another session on analysis problems on design of compression members. Today we'll try to complete analysis problems, then later in the next session we'll try to move for the design problems. There are different types of design problems in this design of compression members. We'll see later. So today our first problem is a steel column is 5 meters height, right, with both the ends restrained, against translation and rotation. See, as per table number 11, page number 45, if you go through, if it is restrained against translation and rotation about both the ends, it is nothing but it is a fixed end. Okay, both ends fixed. Okay, it is built up of an ISHB 400 at the rate 822 Newton per meter with 2 cover plates of 400 mm by 10 mm size, one on each flange, connected by fillet welds, okay, along the length onto the edges of flange. Take Fy as 340 MPa Newton per mm square and determine the design compressive strength, okay, of column. Okay, question, it is very clear. So first we write the properties of ISHB 400 at the rate 822 Newton per meter. Now what this one, this is you will be getting details from what? Steel table. Okay, so if I go back to downloads, SP6 charts. Okay, so here ISHB means it will be in here. ISHB 400 822 means this one. ISHB 400. What is the area? Area equals to 10466 mm square. Okay. Next, H is 400 mm. Right. Next, width of flange is 250 mm. Next we required thickness of flange. How much it is? 12.7 mm. Now see here, since he is saying particularly about the built up, because one and two cover plates are placed, you are supposed to write what? Moment of inertia about Ixx and a moment of inertia Iyy. So these two are moment of inertia. How much it is? 28823.5. This is in centimeter power 4 into 10 power 4 will be mm power 4. Similarly 2783.0 into 10 power 4 mm power 4. So this is the data required as per our question. Okay, next I will try to draw the figure so that it will be clearly understood. Okay, this I section, right? On that two plates are placed on the flange at top flange and a bottom flange. Okay, now if I write the dimensions, from here to here it is 400. And what is this? This is 400. What about this one? 250 mm. Next, thickness of flange how much? 12.7 mm. Right? Right. Plate thickness. How much is the plate thickness? 10 mm thickness. Okay. This is the question given. So for that, first, what is the first step? As per our regular thing, effective length of column. From where you can get this effective length means, I remember you, that is page number 45, table number 11 of what? IES 800 2007. Okay, so as I remember, the effective length is nothing but 0.65 L up to my knowledge. Okay, so 0.65 into, what is the L given as? 5 meters, so 5000. So 65% of 5000. So how much it is? 3250 mm. This is the effective length. After effective length, you are going to decide what? Buckling class of cross section. Second step is what? Deciding buckling class of cross section. So again there is a table 10, page 44. As per this table, any built up section, so any axis, the buckling class will be C. Buckling class will be what? C. That you are supposed to remember. Next, what is the third step actually? Calculating the effective slenderness ratio. But here, for calculating the effective slenderness ratio, we required R minimum for a built up section. So in order to calculate the R minimum, one should first calculate moment of inertia of a built up section. Already here given from the steel tables are the moment of inertia about x-axis and y-axis, particularly only for this one, this shaded portion one. Okay, but because of this providing this plate separately on the flange, it has become a built up. So you are supposed to calculate now moment of inertia what? Of built up section. Built up section. Now first about ZZ axis, about ZZ axis. So what will be the about ZZ axis of this one is IZZ of I section plus IZZ of two plates. This is the moment of inertia in general. Now what is the moment of inertia given for I section is 288 23.5 into 10 power 4. As I said you, IXX is nothing but IZZ plus, here the formula is parallel axis theorem, that is 2 of Z is what? IZZ of two plates means B into D cube 10 cube by 12 IG plus area 400 into 10 into H square. H square means from this center to this center. So total from here to here is 400, means half will be 200 plus means into area into H square means 400 by 2 plus 10 by 2 square. This is the thing you are supposed to calculate. If I separately solve this one, okay, 205 square into 4000, right, (168.1) into 10 power 6. Why I have written two plates? Okay, so 400 into 10 cube divided by 12. So 33.33 into 10 power 3. So if I club these 168.1 into e power 6 into 2, so this will be remain same. I am doing stepwise. So 336.26 into 10 power 6, 288 23.5 into 10 power 4 plus 288 23.5 into e power 4. Now whatever the thing you are writing, that you have to mention here clearly in terms of so I got 624.50 in 62450.166 into 10 power 4 mm power 4. Always you have to write with respect to mm power 10 power 4, right? Next, about y axis, for that same IZZ of built up equals to IYY of built up equals IYY of I section, okay, plus IYY of two plates. So what is IYY of section? 2783.0 into 10 power 4 plus 2 into 10 into 400 cube dB cube by 12. Okay, so 10 into 400 shift cube divided by 12 into 2 plus 2783 into e power 4. So how much you got? 134.49 134.49.66 into 10 power 4 mm power 4. Okay, next one is minimum radius of gyration. Minimum radius of gyration means what? R minimum equals to under root of I minimum by A, right? Now what is I minimum? I minimum is lesser of these two values. This you got 624.50, this is 134.49. So this one you have to take. So under root of 13449.66 into 10 power 4 divided by area. Now what is the area you are supposed to take means, where area equals to 10466 plus 2 times of plate also. Okay, so 400 into 10 into 2 plus 10466. How much area? 18466 mm square. So right here 18466, right? So 13449.66 into e power 4 divided by 18466. So you are getting 85.34 mm. 85.34 mm. Next, now you can calculate effective slenderness ratio. Effective slenderness ratio, that is KL by R minimum. What is KL? You calculated here 3250 divided by 85.34. 3250 divided by, so you are getting 38.08. This is the slenderness ratio, right? Next, we'll calculate the FCD value from table number 9C. Next one is what? Design compressive stress, that is FCD. Okay, design compressive stress FCD. You have to refer what? Table number 9C. Why 9C? Because it is a built up section. For that reason you are supposed to take table number 9C. For what FI? Here FI has been changed, that is 340 MPa. Now you visit, what you have to visit now? IS 800 2007. It is somewhat late. You directly go to page number, this is 9C. So for 9C, KL value, R minimum and FCD will write here. What is KL? 38.08, right? So it lies in between 30 and 40. For 38.08, what is the FCD value you are supposed to calculate? Now this is 9C, this is 30 and 40. So for 30 it is 278 and it is 256. So 278, 256, right? Now we'll calculate 278 minus lesser value minus, so 278 minus 256 divided by 40 minus 30 into 38.08 minus 30. Okay, so how much you will be getting? 278 minus 256 divided by 10 into 8.08, 278 minus answer. So you got 260.224 Newton per mm square. Okay, next, design compressive strength. Okay, that is PD equals to AG into FCD. Why I have written AG means gross area of a built up section. Okay, so how much it is? AG, just now we have calculated 18466, okay, into 260.224, right? So into 18466, how much you are getting? That is 4805.29 kilonewtons. So this is the design compressive strength of the given section. Is it okay? Next, we'll solve one more problem, that is channel section connected back to back. Okay. Second question. Two channels, ISMC 400 at the rate 484.61 Newton per meter are to be placed back to back, and used as a column of height 5 meters with one end fixed, okay, and another one hinged, Take Fy as 250 Newton per mm square. Determine the minimum clear distance to be maintained okay, between the backs of channel sections to get the maximum strength. Okay. Also determine the maximum design compressive strength of column. Right? This is the question given. Now, as usual, first we'll write the properties from where? Steel table. So SP6 for I think channel sections. Yes. What is the question given? ISMC 400. Yes. 49. Again, is there anything else? Right, only one is there, right? So ISMC 400. What is the area? Area is to 6293 mm square. Okay. And H anywhere it is 400. And width of flange it is 100. Okay. Next IXX. How much it is? 15082.8 into 10 power 4 mm power 4. And IYY 504.8 into 10 power 4 mm power 4. And one more thing you are supposed to write, that is centroid. Okay. Now where is this centroid? CYY. How much it is? 24.2. Centroid about YY axis, that is CYY equals to 24.2 mm. Now see here, from y-axis the centroid will be lying at a distance of 24.2. So this is CYY. Like that you have written all the given data. Okay. Now as usual, what is that? First step after writing the given data, next one is what? Effective length of column. Okay, one end of the column is fixed and other end is hinged, means you have to go for what? IS 800 2007 table, page number what? 45. So this is the table. Okay, now here, see here, this is fixed, this is hinged, fixed and hinged, that is effective length equals to how much? 0.8 L. So 0.8 into 5 meters, 5000. So how much it is? 4000 mm, 5 heads of 40, 4000 mm, right? Next, second one is what? Deciding the buckling class of cross section. Okay, so again this is as per table 11, page what? 45, and this is as per table 10, page 44. Okay, for built up sections, any axis, the buckling class is C. Okay, any built up member, any or channel section or angle section, whatever it may be, buckling class is what? C. Okay, next, now here especially in the question they mentioned what should be the distance to be provided to maintain, to get the maximum strength. Okay, okay, that is condition for maximum strength. Okay, now first I try to draw the figure. This is one channel section. Okay, this is one more channel section. They are placed back to back. Okay, now from here to here it is CYY, right? Here what condition you are supposed to take means, so from maximum strength of column, the columns are placed such that column is equally strong with respect to both the axis. Means if I change the axis also, means like this or like this, it should be strong. That is IZZ must be equals to IYY, both. Okay, now let us consider the clear distance between this one is S. Okay, Now, how many channel sections are there? So 2 times of IZZ equals to 2 times of IYY. Now here, what is the moment of inertia about x-axis? If I consider this here clearly, if I consider the whole section or individual channel, x-axis will remain same. Suppose if I take only one channel, x-axis is this one, and this one x-axis, and whole section also x-axis is this one. But when I go for the y-axis for this channel section is this, and for this one is this, and whole section is this, means it is varying. Okay, it is varying. In that case, you are supposed to go for perpendicular axis theorem. Okay. Now, if I consider the clear distance between these, what will be this distance? Half of it. And from here to here it is what? CYY. Let I consider this one as H. Okay? Right. Now, moment of inertia about x-axis I can write directly. That is 2 into, okay, moment of inertia of Ix6, 15082.8 into 10 power 4, which is equals to, what is IYY? I have to take IYY of channel sections. Okay, that is, here you will be getting what? Ig plus AH square, perpendicular axis theorem, parallel axis theorem, something is set. Now here first I solve this one. 2 into, what is this IYY? Ig means 504.8 into 10 power 4 plus what is the area? 6293 into H square. Right? I solve here. 15082.8 into e power 4 into 2. So 30165.6 into 10 power 4 is equals to 2 into 504.8 into 10 power 4 plus 6293 into, what is H means? I can write here as what? S by 2 plus CYY. What is CYY? 24.2 square. Okay. Now 30165.6 into e power 4, 10 power 4 is 504.8 into e power 4. This one is how much? 1009.6 into e power 4 plus 6293 into 2, 12586 into S by 2 plus 24.2 square. Okay. Now this one is plus. If I bring this side, it will be minus. So 30165.6 into 10 power 4 minus 1009.6 into 10 power 4 equals to 12586 into S by 2 plus, so 30165.6 into e power 4 minus 1009.6 into e power 4. So how much you are getting? 29156 to 10 power 4 equals to 12586 into S by 2 plus 24 point square. Okay. On solving, that is this a plus b whole square. Okay, a plus b whole square format. If I substitute that one separately, and calculate, I will be getting so 12156 into e power 4 divided by 12586, we will be getting this one. So I will be remaining with s by 2 plus 24.2 square. So I will take this as a root to remove that square. So 152.20 minus, okay, 24.2 into 2, that is 256.00 mm. So this much is the minimum distance to be maintained for getting maximum strength. Okay, to obtain maximum strength. Now this is the part 1 of the question. Determine the minimum clear distance to maintain maximum packs to get the maximum strength. Now we decided this much of distance between the two channel sections will give maximum strength. In the next part we will be calculating what is its maximum strength actually will be obtaining. Okay, now for that, so next is what? Gross area of built up section. That is simple thing, 2 into area of each section. Okay, so 6293 into 2, 12586 mm square. Next, here since IZZ equals to IYY, therefore RZZ will also be equals to RYY. So radius of gyration equals to under root of I by A, that is under root of 2 into 15082.8 into 10 power 4 divided by 12586. So 154.81. Okay, next, effective slenderness ratio. So one end fixed, other end hinge is given. This is, that is KL by R. Okay, what is KL? 0.8 times of L is given as 5000, so 0.8 into 5000 means you are getting 4000 divided by 154.81. So how much? 4000 divided by 154.81. okay, so 25.83. okay, 25.83, right? Next, design compressive stress. What is that? FCD. Design compressive stress FCD. For what FY? for Fi 250 Newton per mm square. Now this is a built up section. You have to visit table number 9C, right? So for KL by R value 20 and 30 by 25 means in between 20 and 30, that is 25.83. and what is the FCD value we'll see now. This is table number 9C. Table number 9C. Okay, for 250 and for 20 and 30 only. So second and third line. So 224 and 211. Right? Now interpolation, 224 minus of 224 minus 211 divided by 30 minus 20 into 25.83 minus 20. So 224 minus 211 divided by 10 into 5.83. So how much you are getting? 216.421 Newton per mm square. Okay, next, last one is design compressive strength. Okay, so PD equals to AG into FCD, right? Now what is AG? Gross area just now we calculated, 12586 into 216.424 into 12586. That is 2723.87 kilonewtons. Means if I provide the distance between the two back-to-back channel sections of 256 mm, I can obtain a maximum of 2723.87 kilonewtons. Okay, so what are the two channel sections we have used? Means ISMC 400, right? I hope you understood both the problems. So with respect to previous problems, here what is the difference between these two problems with respect to earlier problems is, that is, in today's problem and previous problem, in previous problem this is the problem what we have done is same, but the thing is they directly mentioned the effective length there, and they have given two lateral supports for a column section, one at 6 meters about major axis and one at minor axis. That is a previous problem. And what is this one is, here the end condition is given, how both the ends of the column are restrained against translation and rotation, means it is nothing but a fixed condition, that is 0.65 L. Okay, so this is the problem. Next we have solved another problem, that is channel sections placed back to back. Okay, in this question they have mentioned clearly two parts. One is, what is the distance to be maintained between the two channel sections such that it can obtain the maximum strength. So for that reason we have said that if the columns section whose IXX or IZZ equals to IYY, then from that you can obtain a distance such that it can give a maximum strength. So after on calculation of this one, we have got S as 256 mm. If you want the clear detail here, I can solve once again. Now see here from this step I will show you. 29156 into 10 power 4 equals to 12586 of S by 2 plus 24.2 square. So what I can do is S by 2 plus 24.2, okay, is equals to under root of 29156 into 10 power 4 divided by 12586. Okay, so what I get here, 12156 into e power 4 divided by 12586, root of answer. So how much I am getting? X by 2 plus 24.2 is equals to 125.209. So S by 2 is equals to 12520 minus 24.2. So you are getting 128. So S equals to what? 128 into 2. So 256. Like that I got this one. Okay, so after this is the distance to be provided to obtain a maximum strength. Okay, and this is the strength you got. Okay, I hope you understood the concept of these two problems. In the next session we try to start the new topic, that is design problems. All this what we have done is analysis. Okay, thank you.